With this example, we pursue the notion that superposition tables for simply supported and cantilever beams can be exploited for solving more complicated structures. To this end, we consider a beam that rests on a table. The beam length is L, and the length of the table is L over 3. The beam is placed symmetrically, so it bends as shown, and the bending is due to its own weight. And our task is to determine the gap between the beam and the table in the middle of the table, or in the middle of the beam. As usual, we assume that EI is constant. Now, this beam could be represented as a more familiar model where the weight is represented by a uniformly distributed load, lowercase w, and of course this load, as the weight per unit length, is simply equal to the weight divided by the beam length. So now our task is to calculate the deflection in the middle of this beam, and of course we expect that this deflection will be negative. So we approach this problem by simply observing that the midspan is a simply supported beam, but the two overhangs that kind of prevent us from using the tables directly. And so it's natural to get rid of the overhangs, and we do it by cutting to the left of this support and to the right of this. And here's what we get. We get this wing and this wing, because of symmetry, they are mirror images of each other. And as a result of cutting, I expose the shear force and the bending moment. And of course, these forces, by the third law, applied to the midspan. And now I can see that the midspan is subjected not just to its own weight, but a pair of forces P and a pair of couples M0. The value of M0 and P is easy to find by looking at this free body diagram. So sum of the forces implies that P is equal to W over 3, and M0 could be computed right away by taking some of the moments about this point. Let me observe that if the beam were not symmetric, the forces on this overhang would be different, but calculating them would not be a problem. All I have to do, I also will take into account this free body diagram, write down equilibrium equations, and proceed as with the symmetric case, right? Of course, because of symmetry, I really don't need to do it, so I can focus just on the left wing. Now, let me focus on this beam. So let me redraw it, emphasizing that this beam is subjected to the uniformly distributed load, two couples, and two vertical forces at the supports, and all of these loads are explicitly defined. So what I will do, I will now decompose this case into three cases. 1, 2, and 3. And for each of these cases, I can use the tables. Case 1, a load, a uniformly distributed load. Here's the table. I'm interested in computing the deflection in the center, and it is given by this equation. All I have to do is to replace Q with lowercase w, L with L over 3, and that's the answer. I write it in terms of the weight. And now, let's look at the case. Have two couples. Fortunately, the tables give me the solution for two couples. I want to pay attention that in the solution, this couple is clockwise, this counterclockwise. In my case, it's in reverse, so this is counterclockwise and this clockwise. Therefore, when I use this formula, I will put minus sign. And here's what I have. 1 over 8 minus, of course, WL over 18, the length, squared divided by EI, and I have minus 1 over 1296. So the couples lift the beam up. Now, the next case, two forces. There are no tables. The reason there are no tables for this is actually very simple. These two forces, all they do, they induce reaction forces, but they don't bend the beam. Right? It's very easy to see that at each reaction, the support the reaction will be W over 3, and so there is no bending moment, and so therefore there is no bending. And therefore, the deflection due to the pair of forces is equal to 0. Finally, I can put it all together. So here's my original center span, 3 cases, and now I put together delta C. The first term is from the distributed load. The second term is from the couples. The third 0 is from this case. When I put together, I obtain that delta C is equal to 7 over 10,368 WL cube over EI, and of course minus was expected from the very beginning because minus indicates that the beam deflects upward, and so if I disregard minus, I get the value for the gap